In this video we'll go over the simulation of the bipolar transistor with two sort of bias settings. In the first bias setting here, the voltage, the bias voltage is at 0.7 volts, and the second bias setting, the voltage is at 0.9 volts. So the input in both cases, if you look at it, that's the bias, the DC offset. This is the amplitude, 100 millivolts, 0.1 volts, and 100 hertz. And in this case, 0.9 volt bias, the same 100 millivolt, 0.1 volt amplitude, and 100 hertz. So if I run a transient simulation, the first thing we would look at is what is the voltage here. And so if the input, well, we should first look at the input, so let's do that. So the input amplitude was 100 millivolts, and if we look at the vertical delta, this is the one you are looking at. So if you look at this is the first marker, the horizontal of the first marker, the vertical of the first marker, horizontal of the second marker, vertical of the second marker, and this is the difference between the horizontal, and if you put it for a period, well, here you can't, because the period would start and end at the same point. This is half a period, you get around 200 kilohertz, 200 hertz, which means well, it's just taking this delta t by 1 over this delta t, and also it gives you the slope, but what we are interested in is the vertical delta, so the difference of this and this, and that's around 200 millivolts. So that's your input. And now if you look at the output, there are a few things we can see. The first, that the waveform doesn't quite look the same. It definitely looks a lot fatter here than it looks here, so there is some amount of distortion. And the vertical delta that we are seeing, perhaps we should name this node. 1 second. So we'll call it the emitter 1, or just emitter 1 is fine. And emitter 2. So just run the sim again. So one at the bottom and one at the top, and so the difference here is 127 millivolts, so approximately 63 millivolt difference. Sorry, maybe a little more than that. 64 millivolt is all we are getting, although we are feeding 100 millivolt at VN, we are only getting 60 millivolt at the output. And one more thing we can do here is add a plot pane, and this allows you to see two waveforms at the same time, and this is also useful. So you go here and it switches the thing to the input, and you can see definitely the difference in the curves, where this is distorted and this is not. If we look at the ideal model for the bipolar junction transistor, and I have added it in the site, then we see that we have a nullator here, and the nullator basically is represented by the 0. So this says that the current through the nullator is 0, and the voltage across the nullator is 0, and here I and V can be anything. So then it indicates that if the input voltage here was 100 millivolts, then the same voltage AC wise should appear here. There's also a DC offset which we are not dealing with right now, so this should have been also 100 millivolts. Now this is not the case, so we are going to modify this model with a resistor we will call R emitter, so RE, and then call this the emitter. And not this one. So now the question is, what is the value of this RE? And the resistor RE depends on the current, inversely proportional to the current that the bipolar junction transistor is carrying. So it's actually a VT by the main DC current of the collector, and there's an emitter resistor, and emitter resistor value is VT by IC, where this is the main collector current or the current of the transistor, and VT is the thermal voltage, and its formula is KT by Q, and which is around 25 millivolt at room temperature. So this is in Kelvin, this temperature is in Kelvin, so around 273 plus the temperature in Celsius. So the important thing to note is that it is dependent on temperature, it's not independent of temperature. So this is one parameter to remember, these are constants, and the other parameter to remember, it's inversely proportional to the current of the transistor. So now let's see what was the current in the transistor before. So if I look at I of R3, I'm not interested in the varying part, I'm actually interested primarily in the constant part, and so this tells me that, well, I can even take it on a larger scale. So the average is around 600 microamps. So for this resistance will be 25 millivolts, 25 milli divided by 0.6 milli, approximately 600 microvolts, 0.6 millivolts. So that means these two get cancelled, and this is sort of 2/3, so 3/2 into 25 millivolts, so that's 12.5 and around 37.5. So let's say around 37 ohms in the first case. So that means there is a resistor in series with this 100 ohms of around 37 ohm resistance. So I would be drawing a resistor here. Of value 100 ohms, and the voltage I'm looking at is actually this one, which is a resistor division between 37 ohms and 100 ohms. So I'll get 100 and divided by 137. Well, I can call it 140. I just want to get an approximate number. So that's around 5/7, and that's around 70%. So I should have got 0.7 volt here. I'm getting some 0.64 is what our simulation is giving us. So that's close enough. For your hand calculations, you just want to get an order of magnitude of what's going on, and the rest we can always get from the simulation. And just to check if the simulation is actually making sense or not. Okay, so let's look in the second case here, what's going on. So if I look at the input voltage bias is different, but I can see that it's from 0.8 volts to 1 volt, so the same 200 millivolt input. This is not surprising. And if I look at the second pane, so you click on it to energize it, and here it's from 140 to almost 320. It's almost the full thing back, and we can see that the waveform here is not distorted. So if I take two of these, one at the bottom and one at the top, then I see that this vertical, this is what I'm interested in, is 176 millivolts. So that's almost 88 millivolts, half. The amplitude is almost 88 millivolts. So almost 88-90%. That's pretty good. So now let's see what was the resistance, that series resistance RE. So for that we need the current. So I'm going to click on this pin because I know what that is, and I'm going to get the average current. So that's this. So here I have 2.2 milliamps of current. So this time I have 25 millivolts, the same RE. Maybe that's not the right color to use. So the RE in this case is 25 millivolts. Divided by 2.2 milli, almost 2 milli, a little. So this is 10% more than 2 milli. 2 would have given me 12 ohms, so maybe around 10.5 ohms. So let's call this around 11 ohms. So if you look at this resistor ratio, it's the same 100 ohms, which is the bottom resistor, divided by something like 111 ohms, or even 110 ohms would have given me which is around 90%, right? I'm not equal to, but it's approximately equal to 90%. So this should give me around 0.9 volts, and which is what we see in this in the result, which is around 88 is what we got in our measurement. So now if you look at the output is a resistor. Now for AC purposes, as I have mentioned, the supply doesn't change, so we are only interested in things that change. So as far as we are concerned, this is sort of at ground, and whatever current we are pulling here because of this voltage, the nullator will pull out the same current from the resistor, and if this voltage essentially doesn't move, then the change is negative. So if I apply a positive voltage here, the excursion here would be negative first and then positive. And in both cases this was 100 ohms and this was a 1 kilo ohm. So what I expect to get is that I supplied 100 millivolt, I got 70 millivolt here, so I should get 700 millivolts here in the first case, volt output, and the second case this volt is incorrect, this is a gain, and this is being multiplied by 100 millivolts or 0.1 volt. Well, just to explain that it is being multiplied by it, it's not actually here. This is just a gain of 0.9. When I multiply it by 0.1, it becomes 0.09, and when I multiply it with a gain of 1 kilo ohm, it increases again and becomes 0.9 volts peak. You can also refer AC voltages, you are either referring to it as RMS or as peaks, so we are actually going to refer to them as peak. So we understand that we are talking about this point, this top point. Okay, so we should just look at the output. So we take one pin, we put output there, we take the other pin, we put output there. Now here you can see the excursion part, which is flipped here, because for the bottom window we knew that it was compressing at the bottom, so that's equivalent to compressing at the top here, and this was compressing, this looked fine, and that looks like that. And so if I see that it's 1.75 volts, 1.8 volts, so almost 0.9. And if I look at this one, then this is 1.27, so similar to what we had got before. 0.6 volts is what we are getting at the output for the 60 odd millivolts that we had at the input. So the scaling is fine in both cases, it comes up as 10 each time. But if you look at the DC voltage of the two, so the average value here is 7.7 volts and the average value here is 9.3 volts, and that difference is because the DC 2.2 milliampere is flowing through 1K, so there's a drop of 2 volts, and here it was 0.6 milliamps flowing through 1K, so the drop is 0.6 volts. So I started with a 10 volt supply in both cases. The one last thing I want to talk about is sort of quantifying the distortion, the waveform that's not looking like a sinusoid, and how much of the waveform is not a sinusoid. And if you click on the menu, options actually change depending on which window you are on. So if you click on that window, you can ask for an FFT, and you can ask for an FFT of Vout2 and Vout1. So let's look at this a little more carefully. So you see we have a slightly larger output in Vout2, which was the 0.7 volts to 0.9 volts. So let's try to understand it a little more. So this says it's minus 70, and this says, let's put a marker. So this says it's minus 4 dB. Does that make sense? So to make sense of the FFT, first we should plot something we absolutely know. So that's what I'm going to do. I have put a new voltage source of, well, the AC value doesn't really mean anything. It's a sinusoid of amplitude 1 at 100 Hz. So, and this is the test value. So if I run this simulation, Okay. So I get this image, I click on this and I say view FFT, and I'm on the FFT of test. So this we know is a 1 volt sine wave, and so this should have been 0 dB. So if you remember let's see what we remember out with dBs. So one of the things we know is dB is 20 into log 10 of the signal. So if V was equal to 1 volt, then the dB should have been equal to 0. So the minus 3 dB that we are getting essentially means the FFT is actually plotting the RMS value. RMS value at each frequency, not peak value. So if we look at, for example, the input now, say we in 1, that one, the FFT of that, that's V in 1. So this looks like minus 23 dB, and if you try to make sense of it, it's dB, same thing, 20 into log 10 of V. V is 0.1, 100 millivolt input. So the peak V should have been 20 into log 10 of 0.1, which is 1 over 10. So 10 is 10 to the power of minus 1, so this is just minus 20. And the dB that's being represented here is dB RMS, which is dB peak minus 3 dB. 3 dB corresponds to square root of 2, 1 divided by square root of 2, and that's how you convert in a sinusoid peak to RMS. So we're getting to minus 23 dB. Okay, so that makes sense. That's here. So now if I look at the output, view the FFT, these two, yeah, both of them. Then I find that the one that was 0.9 is sort of 1 more dB below 3, so that's at minus 4 dB, and the 0.7 is almost 3 or little more, 4 dB below the 3 dB. So that sort of makes sense. And more interestingly, if I look at, for example, the harmonic, so this is the second harmonic, here I can see a huge difference. So the waveform that was distorting more is at minus 30 dB, and the other waveform is almost, well, you can just look at it. So again, what we are looking at is the delta. It's almost 20 dB, almost 10 times as clean, or 17 dB. So around 14 times as clean as the other waveform. So the second harmonic is so much smaller in the cleaner waveform. So it gives a sense of how the harmonics work. And distortion is another important aspect of the design.